In this video, we're going to go through diffraction limited resolution, a limitation in a single optical telescope on the sharpness of an image and to the minimum angular resolution between two celestial objects that appear nearby in the sky to be resolved, the lateral separation of which is less than about 1/2 the wavelength used in V-band observations. So we have a diffraction limited resolution. It's basically the sharpness of the image that you can see in the V-band. You're either looking at a single object in the sky or two objects in the sky. So if in the case of the single object, you have two cases. One where the optical case is applying to the sharpness of the single object, and the other case is where you're looking at the sharpness that you can see between two distinct objects. So let's take a look at a cartoon image. And in this cartoon image, we've got an eye, and you're using your naked eye to observe two objects in the sky. So we see two orange stars in the sky, and we're looking for this minimum angle between these two objects that we can see two very distinct objects. So here in this bottom image, we only see one object. Our telescope doesn't have a large enough aperture opening diameter in order for us to see this to resolution. Now this middle image has a bigger diameter aperture, and so we can partially see, but it's not fully resolved. And so finally we have a larger diameter aperture to our telescope, and we're able to see two objects in the sky. So that would be the minimum angle, and that's what we would call the diffraction limited resolution. In this case, we're not using a telescope, we're using our eye. So instead of D being basically the diameter of that telescope, instead the diameter is going to be the diameter of your pupil, because your pupil is acting like the telescope. So there is an equation that relates the minimum angle, theta, so I'll put M here for minimum, because we're looking at this diffraction limited resolution, so we want the minimum. And that is equal to 1.220, the wavelength you're observing in, divided by the diameter of the telescope, or if you're looking with your eye, your diameter of your pupil. Now the original equation that was determined experimentally was by Ernst Abbe, a German optical physicist, and he had come up with something very similar. He came up with D is equal to the wavelength divided by 2n sine theta. And as you can see, we can rearrange this. So let's put sine theta on the left-hand side, and we'll put D on the right-hand side of the equation. So you're going to be left with a sine theta, and that sine theta, is alpha in this case, sine alpha, and that is equal to, we still keep our lambda over 2, our half wavelength, and then we've got this 1 over n number. N is going to be a number. And then we have our 1 over d. So you can see part of it coming in already. You see the d, you see the lambda, and now we've got this 2n down here that somehow converts into this 1.220. So let's go back and take a look at the Airy disks. If you look very closely, you can see these bright fringe circle, dark fringe circle, bright fringe circle, dark fringe circle around each of these. And so the first bright and dark fringe that you see is n equal to 1. And then the next one you see is n equal to 2. The next one you see is n equal to 3. So you have n equal to 1 bright fringe, n equal to 1 dark fringe, n equal to 2 bright fringe, n equal to 2 dark fringe. So you're looking at this fringe. And so you have substitute in here for 1, and experimentally this value of where this dark first fringe appears is at a value of 1.220. So this is the modern day equation that we use, very similar, and we apply a small angle approximation here where sine of alpha is approximately equal to alpha, because you're looking at something very, very far away compared to the diameter of your telescope, say. So this is going to be equal to approximately, sine alpha is approximately equal to alpha. So you can see we dropped the sine and the theta equation, and all we have is our angle theta, which is going to be our minimum angle, equal to 1.220 wavelength divided by diameter of your telescope or your eye. And that will give you your diffraction limited resolution of the sharpness of the image of looking at one object or looking at a couple different objects. Let's say you want to find something like a feature on a single object. Well, that angle that you're going to get is probably going to be the diameter of the angle that you can see of the entire object. And if you're looking for a land feature or a mountain feature on the object, then you probably won't be able to see it if your angular resolution is as large as the object. So you need to find your diffraction limited resolution for your telescope so you have an idea of which objects you can look at and see them crisply and clearly.